Have you ever heard of a Wumpus? Most people haven't. Let me tell you what it is. It's a benchmark that is used to test AI agents in their plannings, automated reasonings, and decision making, specifically in environments that lack observability. It's when they only have partial view of the entire world. The Wumpus World was introduced in 1990. It was first published in 1995 by Russell and Norvig in their book Artificial Intelligence: A Modern Approach. This is actually one of the most popular books when it comes to AI education in universities. The Wumpus World is a controlled environment that is used to introduce and practice logical reasoning, planning, knowledge representation in unspecified unknown domains. It's basically an environment to see how models and AI agents can interact to environments where they don't know stuff for sure. So how does it work? The Wumpus World is a grid. We can always see it as a grid of a certain size. There is always a position where the player starts. For now, let's assume it's here in the corner. There is always gold. This is what the player is trying to find. There is pits. Let's say they're O for now. And most importantly, there is a Wumpus. There's could be one, could be more, but there is always at least one Wumpus. Now the Wumpus smells really bad, meaning that if you're close to them, you can always feel a stench or you can smell a stench in the cells that are right by it. The pits have a breeze, meaning that in the cells around it, you can always feel a breeze coming from the pit. The gold has light, so whenever you're near a gold, you can see some shimmering light in the cells around it. Now, why does this matter? Is because this is the only information you get about the world, but not over all of the grid. You only see these observations in the cell that you're in. So for example, here you would see nothing, you would feel nothing, you would know nothing about the world because you only see information about the grid that you're in. The goal of the Wumpus world is simple. You need to find the gold and make your way back. Of course, if you fall in a pit or get eaten by a Wumpus, you die. Now, the Wumpus doesn't really move from their cell. They're always in the same place. Of course, you can always add it for them to move. It's the same thing for the pits. They always stay the same. And the goal is for you to go to the gold, come back, and get out of the cave. In other iterations of the Wumpus world, your goal is also to shoot the Wumpus. So you also have to know where the Wumpus is and shoot it by an arrow. The arrow is usually given to the player and then they can shoot it in a direction and it goes all the way until it hits something or it just goes away. But let's forget about the arrow for now. Let's just focus on trying to get to the gold. Now, the reason why this is a reasoning benchmark is because the only thing you see again is only the observations, but knowing these observations allow you to reason about the location of everything in the world. Given enough exploration, you are guaranteed to find where the gold is and where everything else is on the grid. Let's use up this example to also see how it will play in a reasoning manner. The idea here is because you don't smell or feel anything or see any gold, you know that all cells around you are safe. So you know that there is nothing here. You also know that because of the cell you started at had nothing because you didn't die, obviously, this cell is also safe. The idea is that you can now use one of the cells around you and move there to make an assumption. So let's say that you choose to go up. When you move up here, you now feel the breeze. Feeling the breeze tells you that there is a pit in one of the locations around you. There is either a pit here, 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 or here. Now, because when you started, there was nothing, like you didn't die, you didn't feel anything, you can also make the assumption that these grids right there, so the one below you, this one, and that one, definitely don't have a pit. The ones on top of you, you don't know for sure. Now, at this point, you would decide if you have an option, you can go back and do this first. So here you can either go to one of these because you know they're safe first, or if you don't have any options, you would choose to make a guess. Now, in this world, you can always go up, down, left to right. So you would only go here, which would be safe, but you wouldn't know for sure. Now, in this world, what you can do, because you know these two are safe, you would go to one of them. So let's say now you go here. Using the same deductions that we just did before, you can now tell that the pit is here, 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 or here. But again, because you know that they are not in any place of that you assumed was safe before, you know that they're not in this one, for example. So the only safe place for you to go right now is to go down. Now that you're down and you're here, you don't feel or smell anything. So now you know that some of the assumptions that you made before were wrong. So now you know that this is safe, and this is safe. And then you can again go and keep doing your exploration. So for example, you come here now for the next step, and now you feel nothing again. So you know that this is safe, and this is safe. And if you do this, just making sure to always pick the safe spot, you are almost always guaranteed to get to the gold. Now, the problem is that sometimes you would have to guess, because sometimes you don't know anything, like I said, other than one of the positions around you contains some danger. Now, if you know how much, let's say pits, how many pits or how many wumpuses for sure are there, you can definitely figure out the locations, or at least figure out more safe positions, knowing that there is only two, for example. So if you know that there's only two pits and you feel a breeze here and you feel a breeze here, then you know that the pit has to be here and then somewhere here. And this allows you to know more spaces are safe. But for this example, the agent does not know how many pits are there, doesn't know how many monsters are there, but there is always one gold. So sometimes the agent will have to make a guess. But in the bigger environments where the model does not need to do any guesses, it is guaranteed to find the gold by just exploring the safe spaces all around. So why does this matter? We recently posted a video about AI reasoning, and I was talking about whether or not AI models, especially LLMs, can actually reason in today's world. And what is the best way to test that than to build an environment specifically made for reasoning benchmarks and test the model on it? The idea is to compare LLMs, reinforcement learning models, and a reasoning-based agents. And maybe we will find out that the best reasoning models are actually models built with if-and-else statements. In this video, I'd like to see if AI models, specifically LLMs, actually struggle with reasoning-based tasks and see how they do specifically on the Wumpus World. When I searched for whether or not the Wumpus World was part of any benchmark testing, I actually couldn't find any real evidence. I also didn't find any papers talking about testing LLMs specifically on the Wumpus World. It could be that it's part of a bigger benchmark that I don't know about, but we're going to see for ourselves how it works internally. For this project, I was able to test Llama and Gemma on a local LLM, but I was also able to prompt GPTs through the browser by giving it all the information that it needs to solve the problem. Now, LLMs have the view of the world because they keep all of the memory in the chat as part of the prompt, meaning that whatever they make an observation or whenever the environment tells them of an observation, they keep track of it in memory. But we'll see that with reinforcement learning model, this is a bit harder to perform. Now, also to make this test a lot easier for me to implement, but also for me to show, the goal isn't to shoot the Wumpus, the goal isn't to go back to where you are, the goal is simply to find the gold. This is because finding the gold, coming back to where you started is easy, and from finding the gold to finding the Wumpus doesn't really change much. So the goal in this step is always just to find the gold, and that would be it. We're going to track how many times each model dies, how many times they find the gold, and the average number of steps they take to make that happen. So let's jump right in. So before we can even do anything, let's start by implementing the Wumpus World as well as a visualizer so we can actually visualize how it looks during training for the different models. We have a screen now that we can visualize, and this purple square is the player. So the blue means there is a breeze, black is a pit, the orange would be the light, yellow is the gold, green is the stench, and finally red is the Wumpus. So we're going to be able to create multiple of these, and we're going to be able to see the models as far as they learn. Now, the first thing that we have to do though is to make sure that the agent, or the player in that case, doesn't see everything, but only sees the stuff that they have, that they can see at the same, let's say, step that they are. But we can also make it so that the agent only sees, let's say, something if they've been there before. But before we jump into AI, I want to jump and talk a bit about why this is a bit difficult for reinforcement learning models. So what we said is that the agent is going to see only the observation on the same cell that they are, right? Meaning that the model is going to be able to here sense nothing. So it's going to be a vector of 0, 0, 0, where 0 is a breeze, stench, and gold. This is how I defined it, and this is how the Wumpus World defines it. So here it will be 0, 0, 0, here it will be 0, 0, 0, and then here it will be 1 for stench and 0 for everything else. Here there's going to be a stench and a light. Unfortunately, we can only show one color in the visualization, so light currently has the most, let's say the higher precedence. And here it will be only a breeze. Now, this is a problem because for reinforcement learning model, if the model is only seeing breeze and 0 everywhere else, it's going to be the same value here, the same value here, the same value here, and here, and here, and here. As you can see, we didn't die because I haven't set it up yet. But the idea here is that the model is unable to find a, let's say, a difference between being here or being here, meaning that it will be always taking the same action. This will be a bit confusing because if the model is here and then it sees that there is a breeze and nothing else, and it takes a right turn, nothing happens. But if the model is here and it sees that there is a breeze and nothing else and takes a right, it dies, and then it gets a very bad reward. Now, this is why for reinforcement learning model, just seeing the, let's say, the observation isn't enough, because reinforcement learning models do not have a knowledge base. By default, their knowledge is statistical, but they're not really keeping track of experiences. So when we're building a reinforcement learning model, we kind of have to make sure we build this memory by making sure that we give it the entire observation. But if we give it the entire world, we are kind of hacking by making the model see everything, including where the gold is and the monster is. But what we can do is give him the observation, but only show the observations in visited cells. So making sure that the model will keep track of the cells that they're visited before. And then this is within every observation. So in a way, we're giving the model the ability to learn and the ability to keep memory and so on. And then from that, we can see how it learns. So let's start by implementing the reinforcement learning now and making sure that we can get this information into the model. Okay. Now we're also able to play the Wumpus World as well. So this is also a nice way to view how the model, we expect the model to reason, right? So this is similar to the example I was showing at the very beginning. Since there is no real percepts where I am right now, that means that all of these are, well, this is awkward. Okay. So this is a nice way to visualize something what I was talking about in the beginning. This is a situation where as soon as you start, you feel a breeze. Now this means that everywhere around you, there could be a pit. This is one of the, let's say, worst cases that you can have, since you now don't know where you can go. And this is a situation where you would have to guess. You would have to make an assumption, and then you would, for example, go up. Now, I see that now because I went up and I feel a breeze. Again, there's one of two options. Either there's multiple pits, or since, for example, if there's only one pit, it will be right there. So right to the right of me right now. But since we don't know how many pits there are, this could be a bit hard to judge. So one of the options that you can do now is either make a new guess, or to, let's say, enforce my assumption by also trying to go here. Now this confirms, since there's like this corner shape, this confirmed that to up of the character right now, there is definitely a pit, and we can confirm by doing this. Now this is a way for just to show how we reason as humans, And it involved a lot of guesswork from my side, where the model would also have to do some guessing if the model doesn't know at all. But for example, here's a situation where I know for a fact that there is nothing, so I know that all of the grids around me are now safe. And because I came from a safe grid, I know that this grid was below me is also safe. But then what I would try to do is also go around here. So now because there is no percepts everywhere here, I know that the extra step here is also safe. And since there's no percepts here, I know that the ones here are also safe. And then you can keep doing this. And then you can build percepts as you go. So here there is a stench. And because I know it's not here, so I know these are safe. And these are safe. So it seems like the breeze and the pit are very close to each other. It's not possible to have either gold monster or gold or pit at the same stop. So there's always only one entity in one cell. And there you have it. We were able to find the gold. Now, unfortunately, the number of steps doesn't count for me, but the goal is to see if models, LLMs, and AI in general can do the same exact thing, or if they will struggle and meet their end. So let's code that in and see how they do. So this is basically the reinforcement learning agent before it learns anything, and currently it's just randomly running about in the entire map. It has no view of the world right now, and again, I didn't really set it up, so it doesn't die when it gets there, but it will die during training, and I will set it up to die later. What we have to do now is actually take that from a completely random mess and train it and see how long it takes it to train, how long it takes it to learn anything, if it will even learn anything. Now, the way this would work is that we cannot really take the model from completely zero information to suddenly put it in the Wumpus world. We kind of have to teach it in very little steps. So basically, the reward for the agent will be that every time it explores a new place, it will get a reward. Every time it finds a gold, it will take a big reward. Every time it dies, it will get a very negative reward. And the idea is to push it towards the gold. So for the very first iterations, I will teach it in an environment with only the gold, where we will also give it a positive reward every time it takes a step towards the gold. And this should teach the model that gold is good and it should go there. It's also important to note that we could teach the model only to see what it's already saw, what happens right now, but it could also be very beneficial to teach the model to act, seeing everything, and then at some point remove the observations. So basically the model will learn what it's supposed to act, how it's supposed to behave when it sees the entire environment, and then we will train it a bit again when the percepts are gone, and then the model will learn in a step-by-step kind of way rather than putting it in the word right away. What we can also do is teach it on the world as it is, but then it will just take longer to train because it will still be trying to figure out what is going on. Okay, so the model is now learning. It's going step by step from a small grid to the big grid. This is currently, like I said, it's seeing the entire map and it's getting a reward every time it gets closer to the gold. And then it will learn that it should go towards the gold in order to get a positive reward. It will also learn that it should not go out of bounds. So the model kind of has to pick on a certain size. Not sure what's happening with the stats here, but that's fine. So the way the model learns for reinforcement learning is that when you build a convolutional network or if you build a fully connected network, you have to decide on a size. For this to work, the model has to always get the same size as input. Now, with convolutional neural networks, the size can vary. It will be a bit harder to implement, but it would be possible. But the idea is to train the model that it could always get 25 by 25 grid. And then whenever the grid is just smaller than 25, everything on the outskirts is now out of bounds. And now it will learn that if it's at 0 and it tries to go outside to the left, or at the top or the bottom or the right of it, it will get a negative reward. So this will also supposedly teach it not to be going out of bounds, so not to make invalid actions. And it should also hopefully teach it not to make a lot of repetitive actions, so going up and down or being stuck in a loop. So most of the time now the model is going towards the same moves, the same amount of times. So it's always going up and then left. But eventually it will probably learn what it can and cannot do. So let's leave it to train and then come back later.
Several days later.
So after 2 days of training and writing code and a day of running everything to check the results, we're finally able to see how the models look like. For this experiment, we now have the logical reasoning, a code that I've written very bare bones to do some reasoning, the reinforcement learning models after it's been trained, the Google Gemma, and then Llama, and finally GPT through the browser. Let's take a look at the 3 LLMs first and see how they compare to each other and kind of see if they do what we expected them to do from the very beginning. Looking at the LLMs, they're exactly what I expected in the sense of that they're slow. I also realized that they're all following the same pattern, usually tending to go all the way to the right and usually repeating themselves over and over again. Now, if they don't get stuck in a loop, usually they do the same thing of just sweeping through with one move at a time until they reach something. So if they start moving right, they go all the way to the right until they hit any percept. And if they go up, for example, they start going all the way up until they hit something, sometimes the wall. And what I also realized is that they're very easy to get into a loop that just never ends. Also realized that GPT, for example, through the browser, after searching for a very long time in the same area, started asking me if we should go somewhere else. And then when I prompted it that it's the one making the choices, it went back into doing the loop. When checking the internal outputs of both Gemma and Llama during their thinking process, sometimes their prompts made no sense because they would assume, for example, that they found the gold, and then they would be like, the gold must be here, but let me check if there are monsters nearby, which didn't really make sense to why they would need to do that. Maybe this is a fault from the prompt side, but I feel like this should be something that is already explained. What I also realized with the LLMs is that they are very keen on taking a lot of chances. So that, for example, they go and see a certain percept, let's say a stench, and then they would be like, I assume the monster must be below me, and then they press down to confirm, where a logical reasoner would say, if the cell is dangerous, let's go search somewhere else. The reinforcement learning model is doing expectantly bad because it didn't really get a lot of times to train. It's also like not very good reward, I would say. I went back and forth quite a lot to make sure I can try to fix it. And I would say maybe with more training, with more working on the reward, it might get better, but it will not be getting anywhere great, which expected. Reinforcement learning models are known not to do any reasoning whatsoever, but rather learn from the reward and keep going. And if you train the model on a specified environment, they will get really good in that environment. But since the environment kept changing every single time, the model really needed, let's say, more time, more episodes to learn better, which I really didn't give it. But it's also something that you would realize that when you're building something that requires reasoning, if you're still waiting for the model to learn how to do it rather than just having a model that is, let's say, ready to do reasoning, it takes a lot more time, which is usually not something that you want to do when there's something that, let's say, can reasons out of the box. So some might argue that this entire test is kind of not great because I didn't give the reinforcement learning model enough to learn, and I'm saying that the LLMs were too slow and they didn't run enough. But to be honest, I feel like it's a good thing to show that AI models by default cannot reason, and that if you want them to reason, you need them to train in a way that forces them to, and then after doing that, like, we can clearly see that the reinforcement learning model isn't really reasoning about the environment, but rather trying to statistically find its way. And since reinforcement learning is just a small, let's say, model compared to LLMs, and they're both trained with reinforcement learning in a certain way, it's just to show that it takes a lot of time and effort to train a model to be able to reason on every single environment, but also it takes a lot of work to make it good. And once you get to the point where you're just statistically doing okay on the environment that you were trained on, this doesn't make you a reasoner in any way. You will still get defeated by a model that just does, let's say, basic thought into what it has to do and builds the environment as it goes. Now, for the sake of completion, I also took in mind that maybe LLMs aren't really good at solving the problem themselves, because once you start prompting them every single step, the context window gets out of hand and they might forget what they were doing in the beginning. So what I also did is ask GPT to generate the code, the logic code that would solve the Wumpus world. I completely explained what was going on, I completely explained everything that was happening in the environment, and I asked it to generate a code that would solve it. Over here we have the comparison between these two, and we can see that while the code definitely runs through more words, it just dies a lot more. That means that the model in some way or form doesn't quite understand what it's supposed to do, because the code, which by the way I prompted back and forth to make sure that it was working, isn't a code that is able to solve the Wumpus world. Now you could go to Claude or whatever is your favorite LLM and try to generate code that works. You can also try to give it the explanation of the same environment that I just gave you and see if the LLM can actually solve it. But this in a way shows that the LLMs, while are good at some reasoning benchmarks, aren't there yet to call them reasoning models. And this brings us to the end of the video. In this video, we showed how different AI models can solve the Wumpus world. We compared reinforcement learning models, LLMs, as well as logical-based reasoners written once by me and once by GPT. And we showed the comparison of all of these AI models and how they solve a problem where they only see partial observability of the world and they're very uncertain. What I wanted to show is that while LLMs and reinforcement learning models and AI in general are really good and really impressive at a lot of tasks, they often fail when it comes to solving problems that require actual reasoning and deduction. This video wasn't about saying one model is particularly good or one other AI is particularly bad, but it's rather about the core point of showing that AI models, while really good, do more of statistical pattern matching rather than actually deduction and actual reasoning to find a solution. Just because AI models get really good at reward optimization and finding out what makes it do good, in the sense of what makes it get the best reward, doesn't particularly mean that they're doing reasoning. The small reinforcement learning model, while wasn't doing that good, and as I explained, just needed a lot more training, LLMs are kind of a very big model that are similar to this oral model. They are trained in the same way, where LLMs are trained also with reinforcement learning, sometimes with verifiable rewards or with human feedback, while the RL models that we had only had a specific reward function that was pushing it to learn how to solve this specific problem, but they both internally work in the same way. It's a neural network that has a specific reward structure and tries to find the best possible way to solve this reward. LLMs and foundation models are way smarter than a small reinforcement learning model, but sometimes we forget that they all work the same way. So if we cannot expect a small reinforcement learning model to kind of reason, why do we expect models that are bigger, trained on more data, to do the same thing? Why can't we also realize that they're, let's say, way smarter because they have more data inside of them, so they have more statistics and more probability in the terms of the things that they do, but they still work the same way. Now, I know a lot of you will start to argue in saying that the LLMs are doing bad because it's either a prompt system or a problem with the way I coded things. I ask you to use your favorite LLM, use your favorite framework or pipeline to run the same experiment and see the results of what you get. I would actually like to see if you manage to make them do better, and we can compare and see where I did wrong. And maybe you realize that some LLMs are actually really bad at reasoning. It depends on how you find the problem. Maybe go and find your own, let's say, reasoning task and see if your LLM can solve it. And then maybe try to think about it. Is it actually trying to sync and deduce, or is it actually just doing some pattern matching? If you have access to the reasoning tokens and the syncing tokens that the LLMs generate, so GPT, for example, don't give you access to them, but if you have a way to see the outputs of the model, also read through them and see if they make sense. I've linked a couple of videos below on some other videos where LLMs are trying to solve a maze by No Hype AI, which I found very interesting and were actually quite of a motivation for me to also do this video. Maybe also give them a watch and see if you can see some relation into this video and the other one. And just remember that the more we understand about how AI does and how it works, and the more we understand that where it succeeds and where it fails, the more closer we get into building better systems. Do let me know what you think about this entire video in the comments below. Don't forget to subscribe if you want to see more, and I'll see you in the next video.